Gradient boosting classifiers. Gradient boosting classifiers are a group of machine learning algorithms that combine many weak learning models together to create a strong predictive model. Decision trees are usually used when doing gradient boosting. Gradient boosting models are very popular because of their effectiveness at classifying complex datasets. Gradient boosting classifiers are specific types of algorithms that are used for classification tasks. As the name suggests, features to this are the inputs that are given to the machine learning algorithm, the inputs that will be used to calculate an output value. In a mathematical sense, the features of the dataset are the variables used to solve the equation. The other part of the equation is the label or target, which are the classes that the instances will be categorized into. Because the labels contain the target values for the machine learning classifier, when training a classifier, one should split up the data into training and testing sets. The training set will have targets and labels, while the testing set won't see these values, won't contain these values rather. Scikit-learn or sklearn is a machine learning library created for Python intended to expedite machine learning tasks by making it easier to implement machine learning algorithms. It has easy to use functions to assist with the splitting of the data into training and testing sets, as well as training a model, making predictions, and evaluating the model. The gradient boosting classifier can be imported via the sklearn library. To perform text classification using the gradient boosting classifier, we import the necessary libraries and packages. Notice that there is sklearn, which is used for splitting the data into training and testing sets, as mentioned earlier. We then load the data. We perform cross-validation for hyperparameter tuning. First, we see the hyperparameters the model currently uses. We currently have 19 hyperparameters the model that currently uses. Criterion, init, learning rate, loss, max depth, max features, max leaf nodes, minimum impurity decrease, and so on are the currently used parameters. We will tune these parameters. We will tune few of these parameters, tree-related hyperparameters. The five parameters we will be tuning are n estimators, that is the number of trees in the forest, max features, that is the maximum number of features considered for splitting a node, max depth, which is the maximum number of levels in each decision tree, minimum samples split, that is the minimum number of data points placed in a node before the node is split, minimum samples leaf, that is the minimum number of data points allowed in a leaf node, boosting the related hyperparameters, the learning rate, that is the learning rate shrinks the contribution of each tree by learning rate. Subsamples, that is the fraction of the samples to be used for fitting the individual base learners. We then perform a randomized search cross-validation. We first need to define the grid. Since we have a huge amount of hyperparameters, we will try a few values for each. For n estimators, we have the values 200 and 800. For max features, we have auto and square root. For max depth, we have 10 and 40. For minimum sample split, we have 10, 30, and 50. For minimum samples leaf, we have 1, 2, and 4. The learning rate, we have 0.1 and zero point 0.5. For subsamples, we have zero point 0.5 and 1.1. Notice that the learning rate is less than 1. If the learning rate is too high, the points may not converge. We then perform the random search and fitting 3 folds for each of the 50 candidates, totaling 150 fits. We find that the mean accuracy of the model with these hyperparameter list is 95.34%, after which we can perform a more exhaustive search centered in those values. Grid search cross-validation. Fitting 3 folds for each of the 12 candidates, totaling 36 fits, we find that the best hyperparameter turns out to have a mean accuracy of 95.57%. Notice that there's a marginal difference between the accuracies, which was earlier 95.34%, now it's 95.57%, that is 0.27% increase. We now fit our model and analyze its performance. We find the training accuracy to be 1, that is 100% accuracy. In the test accuracy, we find it to be 94.01%. The classification report suggests that the average precision is of 94%, the average recall of 94%, the average F1 score is also of 94%. The confusion matrix readings are as such. The business value is of 77, entertainment 47, politics 62, sports 71, and technology 57.